Today I'll discuss rigidity and graphs of groups, and this is joint work with Alex Margolis, Sam Shepard, who's here, and Daniel Woodhouse. So the theme of the conference is subgroups, and given a finitely generated group gamma, rather than study the structure of its subgroups, we want to study gamma by viewing it as a subgroup of some bigger, usually locally compact group, and ask when can it be a lattice in such a group. And so this setup is as follows. Let's a finitely generated group gamma act geometrically on Y, a proper metric space. Then since Y is proper, the isometry group of Y is a locally compact group when equipped with a compact open topology, where a sequence of isometries converge if they agree on larger and larger balls in the space. And in this setting, we say that gamma is a virtual uniform lattice in the isometry group of Y, meaning that the action has finite kernel and the image of gamma is a uniform lattice in the isometry group of Y. And this setup leads to two natural rigidity questions that turn out to be related to each other. The first asks, given gamma, can you classify all of the locally compact groups containing gamma as a uniform lattice? If there are only few up to natural equivalence, then gamma is rigid. And the second rigidity problem asks, if gamma and another group are virtual uniform lattices in the same locally compact group, does that imply the two groups are virtually isomorphic? So let me state these problems more carefully. First, we say that topological groups G and G prime are virtually isomorphic if there exists open finite index subgroups H inside of G and H prime inside of G prime and compact normal subgroups A inside of H and K prime inside of H prime, so that the quotient groups H mod K and H prime mod K prime are isomorphic. So throughout the talk, a finitely generated group is assumed to have the discrete topology. So if you're asking for an open finite index subgroup, everything's open. This just becomes finite index, and compact becomes finite. So this recovers the standard definition of virtual isomorphism for finitely generated groups. Let me give one example. Let's X be the integer tiling of the line, and let G be the automorphism group of this graph, and let X prime be the same graph as X, except with two edges attached to every vertex, and let G prime be the automorphism group of the graph X prime. Then these two topological groups are virtually isomorphic, where the compact normal subgroup is the one that just fixes the integer lattice. So virtual isomorphism is a natural equivalence relation to put on automorphism groups of graphs, which allows you to ignore adding some compact piece, say, to every vertex orbit. And then the first rigidity problem we're interested in is called the lattice envelope. It's due to Furstenberg, and it asks the following: let gamma be a finitely generated group, then classify up to virtual isomorphism all locally compact groups containing gamma as a virtual uniform lattice. And the terminology is that a locally compact group G, the locally compact group G, is called an envelope of the finitely generated group bonds. So this problem is akin to asking given a finitely generated group to classify all of the proper metric spaces the group acts on, but rather than classify the spaces, classify their isometry groups and only up to this natural equivalence. So for example, Mostow's strong rigidity theorem is a celebrated solution to the lattice envelope problem. It's due to Mostow when the locally compact group is a Lie group, and it's due to Furman in generality. And it says that if gamma is the fundamental group of a closed hyperbolic and manifold, and G is an envelope of gamma, then either the locally compact group G is virtually isomorphic to the isometry group of hyperbolic n space, or G is virtually isomorphic to the group gamma, and these are different virtual isomorphism classes. So manifold groups naturally act on hyperbolic n space, and they all act on themselves via a Cayley graph, and the theorem says that up to this equivalence, those are the only geometric actions you get from these groups. And gamma is rigid because it only has two virtual isomorphism classes of envelopes. And maybe a group is even more rigid if it only has one. That leads to the following definition. You say that a finitely generated group gamma has only trivial lattice envelopes if any envelope of the group gamma is virtually isomorphic to gamma. So intuitively, a group has only trivial lattice envelopes if it doesn't act on any spaces that have too many more symmetries than those coming from gamma itself. So for example, Kita proves that mapping class groups of non-exceptional finite type surfaces have only trivial lattice envelopes, and Girdel Bay proved the analogous statements for out of n, for n at least 3. And I'll give other examples of it later in the talk. Let me now state the other rigidity problems that are related to rigidity of lattice envelopes. First, most classically, we say that a finitely generated group gamma is quasi-isometrically rigid if any group quasi-isometric to the group gamma is virtually isomorphic to gamma. So a group is quasi-isometrically rigid if its quasi-isometry class determines a virtual isomorphism class of group. And relatedly, we say that a finitely generated group gamma is action rigid if whenever gamma and another group gamma prime both act geometrically on Y, the same proper metric space. This implies the groups gamma and gamma prime are virtually isomorphic. And in the language of lattice envelopes, this is equivalent to saying a group is action rigid if whenever gamma and another group are virtual uniform lattices in the same locally compact group. This implies the groups are virtually isomorphic. And just note that Milner-Schwartz implies that if gamma is quasi-isometrically rigid, then gamma is automatically action rigid. The converse fails in general. I'll give examples. And in this project, we use action rigidity in certain cases as a key step in proving quasi-isometric rigidity, which was very useful because it's easier to prove a priori action rigidity results because you have some space to work in or some big group to work inside of. Let me start with just a classical example. It follows from work of Tukia, Gabay, and Kassin Younggrace. That's the fundamental group of a closed hyperbolic surface is both quasi-isometric and therefore action rigid, but this fails in higher dimensions. The fundamental group, for example, of a closed hyperbolic three-manifold is neither. Since there are infinitely many commensurability classes of closed hyperbolic manifold groups acting on hyperbolic pin space. So this project concerns rigidity in graphs of groups. So let me start with the free product case, or the infinite-ended case in general. So first note that quasi-isometric rigidity, quote unquote, often fails for the following reason. Papasoglu and Whyte proved that the quasi-isometry type of a free product depends only on the quasi-isometry types of the one-ended factors in the free product decomposition. So there's a huge amount of flexibility to build quasi-isometric groups from free product constructions. But on the other hand, multiplicative invariance can be used to build non-virtually isomorphic free products, where a multiplicative invariant for a family of groups is a number assigned to each group that's multiplicative with respect to index of finite index subgroups. So like Euler characteristic or L2 Betti numbers. So for example, using recent work of Lazarovich, let's, for I between 1 and n, let's Gi be a one-ended hyperbolic group. So Near produced a multiplicative invariance among the family of hyperbolic groups that's non-zero for every hyperbolic one-ended hyperbolic group. And he'll talk about that in this conference, I think. And for the application, we require that Gi has a finite index subgroup, Hi. Then the free product of G1 through Gn is not quasi-isometrically rigid because by Papasoglu and Whyte, this group is quasi-isometric to the free product of H1 through Hn, but you can use the multiplicative invariant to show that these groups are not virtually isomorphic. So in this sense, quasi-isometric rigidity often fails for free products, since any free product of one-ended hyperbolic groups with finite index subgroups is not quasi-isometrically rigid.
That's a proper finite index subgroup.
Yes, thank you. Yeah, at least one has to be, for at least one, I think. Yeah, and I guess at least you just need one of these to have a finite index. Okay. So the main theorem I want to discuss. Yeah, thank you. Yeah. Thank you. Thank you. Yeah, thank you. Okay, so this is joint work with Alex Margolis, Sam Shepard, and Daniel Woodhouse. And the point is that we show that action rigidity often holds for free products as long as you assume rigidity of the lattice envelopes in the free product decomposition. So let me state the theorem and then define the main term in it. So let gamma be a finitely presented, virtually torsion-free free product of graphically discrete. Then gamma is action rigid within the family of virtually torsion-free groups, meaning that if gamma and another virtually torsion-free group act geometrically on the same space, then the two groups are virtually isomorphic. So graphical discreteness is a rigidity condition on lattice envelopes, and let me define that now. Okay, so first, discreteness. For what follows, let's X be a locally finite graph that admits a co-compact group action. Then the automorphism group ought to X is discrete if the compact open topology is the discrete topology. And this is equivalent to asking that's no non-trivial sequence of automorphisms converges to the identity automorphism. So to give an example and a non-example, the automorphism group of the 4-valent tree is not discrete, since there's a sequence of automorphisms fixing larger and larger balls in the graph, but just permuting branches outside of the ball. But on the other hand, the automorphism group of the integer lattice tiling of the plane is discrete. If an automorphism fixes a non-trivial ball, it fixes the whole graph. And we'd like to define a group invariant, and note that it's too much to ask that whenever a finitely generated group acts on the graph has a discrete automorphism group, because you can always take such a graph and build a new one by adding 2 edges to every vertex to get a new graph X prime. So instead we ask for this property, but only up to virtual isomorphism. So let me say that in a slightly different way. The automorphism group of a graph X is compact by discrete if the group has a compact normal subgroup so that the quotient has the discrete topology. And as long as there is a co-compact group action, this is equivalent to asking that there exists some constant A greater than 0, so that for any 2 vertices, V and X in the vertex set of the graph X, the size of the orbit of X under the stabilizer of V has cardinality bounded above by A. So in other words, you ask for any vertex V, if you look at the orbit of any other vertex, that orbit has size bounded uniformly by a constant A. So for example, the automorphism group of the tree is not compact by discrete, because if you fix the center, size of orbits tends to infinity. But this graph X prime does have a compact by discrete automorphism group. I think size of orbits is bounded by 8. So finally, we define a finitely generated group. Gamma is graphically discrete if whenever gamma acts geometrically on X, a locally finite graph. The automorphism group of the graph X is compact by discrete. And this is equivalent to asking that the automorphism group of the graph X is virtually isomorphic to gamma. So this is saying that a group is graphically discrete equivalently if its totally disconnected lattice envelopes are all trivial. And it turns out, just considering spaces the group graphs the groups act on, having compact by discrete automorphism groups is enough for the other rigidity problems we're interested in. So let me give some examples.
So your reasoning, this X here with an incountable group, but this virtual isomorphic lets you say this uncountable group action is pretty much like your vanilla.
Yeah, that's right. So gamma doesn't act on any graphs that have too many more symmetries than those coming from gamma. And so I just erased it, but a free group is not graphically discrete because it acts on the tree, which does not have a compact but discrete automorphism group. So the difficulty in general in producing examples is that you have to understand all actions of your group on some locally finite graph.
Compact in this compact, like it does to stabilize out some finite set.
So like in that the integer lattice example, it's this stabilizer. It's the subgroup that fixes the integer lattice. The whole thing. Okay, so examples. It follows from work of Botter and Ansauer. That's the fundamental group of a finite volume, hyperbolic, and manifolds for n at least 3, and the fundamental group of a closed hyperbolic surface are all graphically discrete because their lattice envelopes are classified. Their results are more general. It follows also that lattices in PSL and R for n at least 3 are graphically discrete. It follows from work of Trofimov that's virtually nilpotent groups like z to the n and the integer Heisenberg group are graphically discrete. So in that example of the z-squared acting on the plane, it was possible to show that, that automorphism group was compact but discrete. Trofimov proves it's true in general. I don't know a simple proof of that fact, and I would like to, even, I believe, for n at least 3.
Non-uniform.
Non-uniform and uniform, yeah. Combining the results with work of Dymars on lattices in Sol and work of Popovich and Lieb on groups quasi-isometric to H2 cross R, it follows that the fundamental group of a closed geometric 3 manifolds is graphically discrete. Another source of examples come from groups with only trivial lattice envelopes in general. So mapping class groups out of n are graphically discrete. We show that the fundamental groups of closed non-geometric 3 manifolds fit in this category and are therefore graphically discrete. And let me give one last example that follows from work of Barb and Mosier. That's hyperbolic surface by Greek groups are graphically discrete. And this is open for hyperbolic free by free groups or hyperbolic free by cyclic groups that don't split over the integers. And that's a problem I'm very interested in because it gives one potential route to proving quasi-isometric rigidity for those groups. All known models for free by cyclic groups have discrete or compact by discrete automorphism groups, but I don't know how you show it for any possible model for those groups. All right, so let me now make the connection between this kind of lattice envelope rigidity and quasi-isometric and action rigidity theorems. So first, it follows pretty easily from the definition that if gamma is graphically discrete and gamma and another group, gamma prime, both act geometrically on the same locally finite graph, that's gamma and gamma prime are virtually isomorphic. So in proving action rigidity theorems or quasi-isometric rigidity theorems, the hope is to upgrade a quasi-isometry or an action on some space to an action on the same graph. And together with graphical discreteness, that gives the virtual isomorphism. And this is actually achieved by Margolis in very great generality recently. So it follows from his work that if gamma is graphically discrete and intuitively, if gamma is not like a Baumslog solitaire group and is not a lattice in certain Lie groups, then gamma is action rigid. But maybe to say this correctly, if gamma has no infinites commensurated subgroup that's either free abelian, so this is like a Baumslog solitaire group, or a uniform lattice in a connected center-free semi-simple Lie group. Outside of these two special cases, gamma is automatically action rigid. Because, yeah. Like a closed hyperbolic 3-manifold group is not action rigid, and this rules out similar examples. Right, so Alex proved that if you have a group outside of these two classes, and that group and another group act on the same proper metric space, then they act on the same graph. So if you add graphical discreteness, you automatically get actions.
You said there were action rigid ones that weren't UI rigid.
Like the free product of two closed surface groups.
That's just in, center-free, semi-simple,
Without compact factors.
yeah, so what about say something like say SL and QP or something like that, so they do have this.
I'm not sure. I'm not sure. There might be an asterisk. I think this is correct, but I'm not sure. Okay, so our action rigidity result for in general concern graphs of groups that are usually themselves not graphically discrete. So Alex's results don't apply, but they're built from groups that are. So let me outline the proof of our theorems and give an additional example outside of the free product setting. Okay. So this is kind of a general blueprint for an action rigidity. So let me recall the setup for free products. Suppose that you have finitely presented for the torsion-free free products gamma, which is the free product of gamma 1 through gamma k, and gamma prime, which is the free products of gamma 1 prime through gamma L prime. And suppose these groups both act geometrically on Y, the same proper metric space. And suppose that all of the gamma I and gamma I prime are one-ended, and crucially that gamma I is graphically discrete for each I. Then the proof has two steps. First step is to promote the common model geometry to show that the groups gamma and gamma prime both act geometrically on X, which will be a simply connected cell complex with a natural tree of spaces, decomposition mimicking that of gamma and gamma prime. And then there are two compact graphs of spaces that are quotients under the action of gamma and gamma prime with fundamental group gamma and fundamental group gamma prime. And the goal is to prove that in this case, these groups are commensurable, and that's achieved by building a common finite sheeted covering space of these two compact graphs of spaces. Step 2 is a common finite covering space argument using one of the recent generalizations of Layton's graph covering theorem, particularly variance due to Shepard's and Gardam Woodhouse are relevant in this step. Okay, so this proof strategy and holds for more general graphs of groups than just free products. In general, for step 2, you need additional algebraic assumptions on the images of edge groups inside each vertex group, notably the commanding assumption that Sam will discuss during the Cubes week, Cubes conference. So let me say more instead about step 1. What is the common model geometry construction and how is it useful? This is our general common model geometry construction. So suppose G is a locally compact group. This will be applied when G is the isometry group of the metric space Y, the original model geometry. And suppose that G, the big group, acts continuously, minimally, and co-compactly on a tree C. So in the free product case, Y is infinite-ended, and work of Cornulier proves that the full isometry group of Y also acts on a tree. And you have to make two assumptions on the stabilizers, vertex and edge stabilizers of G acting on the tree. So suppose first that vertex and edge stabilizers of G acting on the tree T are not finitely presented, but are compactly presented. This holds whenever you assume vertex groups are finitely presented. And the second condition is the key one, that vertex stabilizers are compact by discretes. And the second condition is exactly what graphical discreteness buys you by definition. And then the conclusion is that the big group G, the locally compact group, acts geometrically on xt prime, a tree of spaces, with two analogous conclusions. First, a vertex and edge spaces that are simply connected cell complexes, and B, that the action of every vertex stabilizer GV on its corresponding vertex space XV is discrete. So let me sketch a picture on the sideboard. Okay, so the conclusion of the theorem is that you have these two finitely generated groups, gamma and gamma prime, that are subgroups of the isometry group of Y, which is some locally compact group G. And the theorem says that G, and therefore these finitely generated groups, everybody acts geometrically on some tree of spaces. Or in the free product setting, the free product factors stabilize one of the vertex spaces in this big tree. So for example, if the centerpiece is a vertex space XV, then there are some factors, gamma I and gamma J prime, that acts geometrically on this piece, XV. And what the conclusion gets to is that since GV acts on XV discretely, these two groups, gamma I and gamma J prime, are commensurable, the isometry group of the vertex space XV. And this is exactly what allows you to build common covers of the vertex spaces. So the point is that we're trying to run a common cover argument, and you have two compact graphs of spaces. So the first step of the argument, which is allowed by the model geometry theorem, is to build common covers of the vertex spaces in some pairings. Step two of the argument, which needs Layton's theorem, is to glue these pieces together coherently to get some common finite cover of both graphs of spaces. Yeah.
I think I missed or forgot how you explained in this setting how you get from these assumptions of these two groups acting in Y to the isometry group of Y acting in free.
It's Cornulier. It's proof. Yeah, I think there's
Make it to be free products or just
infinite-ended. Infinite-ended. Yeah, Y should be infinite-ended. Then the isometry group of acts continuously on a tree. Okay. So let me remark that I found it very useful to me to work in a locally compact group setting, which was new for me in this project. And it was useful for two reasons. First, this proof unified many individual arguments we had that required extra assumptions. Like we had a proof for free products and a proof for being hyperbolic and splitting over in a certain way. And I think this framework generalizes all of those ideas in a nice way. And secondly, the proof itself uses the tools from locally compact groups. So the constructions of variants of the Cayley-Abels graph for a totally disconnected locally compact group. Okay. All right, so in the last few minutes, let me give one other application of these proof techniques outside of the free product setting.
Can I just ask, what do you mean by the active discrete?
The image of GV in the isometry group of XV is discrete. Okay, so let me give a second sample application of these techniques. So let's gamma be the fundamental group of a graph of groups. So that's three conditions hold. First, the vertex groups are graphically discrete, hyperbolic, and co-compactly cubulated. And B is a condition on the image of the edge groups in each vertex groups. So the image of all incident edge groups in a given vertex group is an almost malnormal family of infinite quasi-convex subgroup. And the third condition, C, is that the Passer tree of spaces is preserved by quasi-isometries. I'll say what that means in a second. Then this graph of group, the fundamental group of this graph of groups gamma is action rigid. So graphical discreteness is needed in all of these theorems. The other assumptions, being hyperbolic cubulated and the conditions on the edge groups, are needed to get the common cover arguments to work that Sam will discuss. And C is the condition that you need to get the big locally compact group acting on a tree. So when you build the natural tree of spaces for this graph of group, the universal cover, you want that every quasi-isometry preserves all vertex and edge spaces up to bounded Hausdorff distance. In those cases, you can conclude that gamma is action rigid. And let me end with one example, explicit example.
This condition, see that you put that's automatically guaranteed if you're.
The JSJ, or is it? Yeah, it's automatically. If your graph of groups is coming from a JSJ decomposition, then condition C is automatically. Yeah, that's a good example. That's the first example. So let me end with two examples. Let's M and M prime be closed hyperbolic three-manifold. And let's gamma be the amalgamated free products of their fundamental groups over the integers where a generator maps to non-proper powers on either side. Then gamma's action rigid. And a second example, let gamma prime be the fundamental group, the amalgamated free products of these two groups over a free group where the free group maps to almost malnormal quasi-convex subgroups on either side. Then both of these groups, gamma and gamma prime, are action rigid. By the theorem, in the first case, the Passer tree is preserved by quasi-isometry since this is a JSJ decomposition. And in the second case, that follows from work of Mosher, Segev, and Whyte. But I include these because the quasi-isometry groups of these gamma and gamma prime are very different. So we're able to upgrade action rigidity to quasi-isometric rigidity. This group gamma prime is quasi-isometrically rigid. But in the first case, whether these groups are quasi-isometrically rigid is open. I think our tools seem to get you very, very close. I think we all think it's true. And this is an open problem I like a lot. So
Thank you. Does anyone have any questions?
So how do you upgrade the action rigidity to QI rigidity? How?
yeah, so Margolis proved that if you have a hyperbolic group that's action rigid and has the uniform quasi-isometry property, which means there's some constants K and A, so that every quasi-isometry is close to a Ka quasi-isometry, then you can upgrade action rigidity to QI rigidity. So that holds for these groups, it fails for these groups. It's a very strong property in general, but you probably don't need it to upgrade. Yeah.
How hard would it be to like the first and
You need it for this commanding hypothesis of Sam's. So really the right condition is being commanding, which I won't define. I mean, I can define after for you, but that's what virtually torsion-free gets you for free products.
Are surface groups action rigid?
They are because they're QI rigids. Well, yes, all surface groups are.
Okay, well, there are no more questions. Let's thank Emily again.